how to measure the height or altitude of the sun on the equinox using a right isosceles triangle. All right? So, on the equinoxes, March 21st and September 21st, around there, the sun is directly above the equator. And it is also at a 45-degree angle to the 45th latitude north and the 45th latitude south. And those two 45-degree angles combined with the sun's angle to those two 45th latitudes makes a right angle on the top. So you get a right isosceles triangle, which happens to have equal lengths on the two legs coming off the right angle, because it's got right angle and two 45-degree angles. All right. But the other thing about a right isosceles triangle is that the height is twice the length of the base, right? So if latitude lines are 69 miles apart and you've got 90 of them, then 69 times 90 will get you 6,210. All right, so if you cut that in half, 3,105 would be the height of the sun, right? Because you could just use the one right triangle that's on the equator, 45th latitude, and the sun. And the right angle would be at the bottom on the equator. And then you'd know it was a 45-degree angle, so you'd know that the distance from the equator to the 45th latitude was the same as the distance from the equator to the sun's altitude above the equator. But that would be, a lot of people would argue, well, that the sun's a light in the sky, it's hard to say. But when you look at it from both sides, all right, because if the sun was at a 45-degree angle and it's right over the equator, it's a closed case. But some people would argue, oh, the sun's 93 million miles away, which would mean that the sun was actually way away. But if you're at the south latitude, 45-degree latitude, and the sun's at a 45-degree angle, and you're at the north latitude and the sun's at a 45-degree angle, then it has to be at the same point where those two angles cross above the equator. Otherwise, there would have to be two suns, one way off 93 million miles to the south and one 93 million miles to the north of the triangle. If you continue the 45-degree line out into like an X pattern. So don't try and then don't turn around and try to use trigonometry to say, all right, well, if I'm at 45-degree angle, then go out to a 60-degree angle and add that many more 69-mile latitudes, because trigonometry doesn't work that way. You will not get the results that you're looking for, unless you're looking for a result to try to prove that the Earth is a globe, right? But look, trigonometry isn't based on a globe, right? So using trigonometry to say, oh, your flat Earth math doesn't work is just a cop-out, because what you're effectively saying is that right triangles, when you calculate the tangent, right? Because that's what you look, the trigonomic function of finding the height of the sun when you know the base length and the angle is 45 degree angle, the trigonomic function is tangent 45 equals adjacent over, or opposite over adjacent, TOA, right? Tangent 45 equals opposite over adjacent, and you're looking for the opposite, and then you can pare it down, and that should yield the number. But really, with a right isosceles triangle, you're better off using the Pythagorean theorem. You're not going to have to, because you already know it's a 45 degree angle, it's a right angle, and therefore the other angle is 45 degrees, and both of the legs are of equal length. So if you know one of the legs, you know the other leg. You know what I mean? You can't argue with that. And then when you put two of them back to back, one at 50 south 45th latitude, and the other one at north 45th latitude, with the sun at the pinnacle and at a 90 degree angle, then the base becomes twice the height. All right, so then you've got, it's 6,210 miles from the 45th to the north to the 45th south latitude line, and therefore the sun is half of that length above the equator. You also can't argue that. All right, so that's the crust of the biscuit, and that is where you start. Now you've defined the height of the sun. Now you know the height of the sun. So if you want to figure out how far away a degree is, some arbitrary degree, start with the height of the sun, because you've already established that. Don't try to reprove what's already incontrovertible by changing the angle and the distance, and then now the sun's a different height. Look, however you measure the height of a building, maybe you have to go twice and measure it to degree off, and then you measure the difference, and then you use your triangle math. That's how it works. It's the same way. Just because the sun is the sun doesn't change the laws of triangle math. So don't say that triangle math makes buildings a different height depending on how far away from them you are, because that's what you would be saying if you said it does that with the sun. It's the exact same thing. When you punch in trigonometry on a calculator, the calculator doesn't know whether you're talking about the top of a building, top of a mountain, or the sun, or the corner of a piece of wood, right? So it's a Pythagorean theorem and a special right isosceles triangle. Those are the tools that you can use to establish the sun's altitude. And then after that, you can calculate whatever you want, but you can't try to double prove something that's already just completely established with a double proof. South latitude, 45 degree angle, north latitude, 45 degree angle, wherever that is. It's said to be at the 45th latitude. But wherever a 45 degree angle is, if you measure from there to the equator, when the sun's above the equator, you will get the height of the sun, because the two legs of a right isosceles triangle have equal lengths. Closed case.